I'm Mike Widico. I'm with Cottrell. We're members of ICAC, and I've been asked to say a few words today about fabric filters. Fabric filters, there's lots of them in use. They're used for lots of different applications. Tell you a little bit quickly about my background and perspective because it influences what I say today. Not that you're so much interested in my resume, I know you're not, but I've had more than 30 years of experience with fabric filters and dry scrubbers of various designs. I have been mostly focused around engineered filters, process filters for particulate control and for combination acid-gas particulate control. So most of my paradigm, my perspective comes from the power industry, incineration industries, metal, cement industries. So that's going to put a spin, I guess, on what you hear from me today. What is a fabric filter? A fabric filter, essentially, it's an industrially sized vacuum cleaner. You take the gas containing the particulate and you either blow it or draw it through across a fabric surface where the solids are removed from the gas. You collect it on the fabric surface, and then the accumulated solids are periodically discharged from the bags into hoppers through a variety of collection devices. There's a typical fabric filter that my company built for a steel application. Fabric filters tend to be gaining prominence in particulate control versus electrostatic precipitators, and I think John did a very nice job of describing ESPs, and some of the questions focused on some of the differences, and just in all candor, my company also makes a lot of electrostatic precipitators as well, so we have some background there as well. But the advantages of fabric filters compared to precipitators is the ability to achieve lower outlet emissions in a more cost-effective manner. Some of the discussion previously revolved around getting down to low emission rates. My ESP guru in my company will tell you that you can make a precipitator get down to just about any emission rates. The problem is you keep adding treatment time and collecting area, and the box becomes enormous. So with a fabric filter, you're able to do that in a more cost-effective fashion. Another key advantage is filters can more easily accommodate changing inlet conditions. ESPs are very, very specific devices. You design them for flow rates and ash chemistries, and there's an art to all of that, to making them work correctly. But if you change the inlet conditions, you will change the performance of the unit very easily. You change the temperature, you change the ash chemistry. For instance, in the power industry, over the last number of years, you've seen a lot of operating coal-fired units that were designed to burn high-sulfur coals and had precipitators built for low-resistivity high-sulfur coals switch to PRB. PRB has a high resistivity ash, and that impacts the performance of the ESP, so that needs to be taken into account. Also, fabric filters have the ability to function as gas solids reactors, and that's become increasingly important, especially as the newer rounds of regulations are not just issued on particulate control. The MATS rule, the MAC rules, contain a number of, you got to remove acid gases as well as particulates. So the back end becomes a combination device, and because of the inherent gas solids contacting, the filters function fairly well as reactors, either as primary or secondary reactors. The disadvantage is you will take a higher pressure drop, where an ESP, typically flange to flange, you're looking at a 1-inch pressure drop. With a fabric filter, you're looking at 6 to 8 inches flange to flange, typically. So you will take a higher pressure drop, more energy consumption, and you have temperature limitations. The interior of an electrostatic precipitator is typically all metal. So you can take changes in temperature, you can take higher temperatures. There are hot side electrostatic precipitators that operate 700 plus degrees. In a fabric filter, you're limited by what the bags can take. And typically, right now, that's, with fabrics, probably a continuous operating temperature in a range of 500 degrees Fahrenheit. So in a power plant, it forces you to the cold side of the air heater. And if you've got processes that are subject to having sparklers or sparks carryover, that's a problem for the bags. Bags burn, and they don't work well when they burn. Whatever material you put in there as a filter media is going to have to be changed periodically. Bags last, depending on the application and whatnot, probably somewhere in the range of 2, 3, 5 years, more or less. I mean, there's data out there that goes outside that span, but you will have to eventually change the bags. So that needs to be taken into account. There are lots of types of fabric filters out there used for all different applications. Smaller ones, standard catalog filters, cartridge filters that are typically used for nuisance dust control. If you're venting a silo or you've got a transfer point, things like that, your dust is going to puff and you want to collect that so you don't have a fugitive emission. My background, as I said, is more in process filters, treating flue gases, kiln gases, metals, furnace gases, that type of stuff, and I'll talk more about what's going on there today. There also are some other things that are going on. There are hybrid filters, Copac type devices that are half precipitator, half fabric filter that are useful in certain retrofit applications in particular. Take the best features of both technologies and combine them. They're ceramic filters. The filter media itself doesn't necessarily need to be fabric. There are more exotic materials out there that allow you to operate at higher temperatures. They've got their pluses and minuses, so I'll touch on that. Process filters, there's really have been two common fabric filter designs, the reverse air units or reverse gas units, where the dirty flue gas flows on the inside of the bags. Solids are collected on the inside. Clean gas goes to the outside, exhaust to the stack. They generally have filtering velocities or air-to-cloth ratios in the range of 2 cubic feet per minute per square feet of collecting surface, and this filtering velocity, as many of you know, is sort of a key sizing parameter for filter performance. Bag diameters typically range from 8 to 12 inches. Bag lengths as high as 36, 39 feet. You have to hang these bags individually. So they tend to take up a lot of room. They've got a large footprint, and they're typically field directed, which means when you're putting one of these things up, there's a high labor component to putting it together. They're shipped, knocked down, and you have to assemble them in the field. What's developed now more commonly are the pulse jet units, where flue gas, the dirty flue gas, flows on the outside of the bags. Particulate collects on the outside, the clean gas flows through the inside and exhausts. Those bags have to be supported, obviously, so they don't collapse. You can operate with higher air-to-cloth ratios in the range roughly of 50% to twice what you can with a fabric filter, with a reverse air unit. So that means less total bag area, fewer bags, smaller space. The bag diameters tend to be smaller, 5 to 6 inches in diameter. But bag lengths now, and this has been one of the developments over the past 10 years or so, have increased quite a bit. It used to be the old high-pressure pulse jets could only effectively clean a bag that was maybe 16 feet long. Now with some of the advanced cleaning mechanisms that have been developed, bag lengths have steadily increased, 7 meters, 8 meters. There's quite a lot of experience, particularly in the power industry, with 8-meter bags now. They've gone up to 10 meters, and I have heard from some of the bag suppliers that in Australia they've gone even higher than that. They're getting very long. So particularly for retrofit applications, space is always at a premium. And if you're trying to retrofit a device into a plant that was built 30, 40 years ago and wasn't contemplating this device, there's not a lot of space. It's always cheaper to go up. So they have a more compact footprint, and in many cases they're modularized. You ship the whole module. You can shop assemble a whole module. The tube sheet down through the hoppers, bring it in, drop it in place, put the bags and cages in. hook up the cleaning system. So it really cuts down on the field erection time and the costs associated with that. So the pulse jets have pretty much become the standard for many industries now. Some of the recent trends that we're seeing in fabric filters mentioned is this low pressure pulse or medium pressure pulse that allows you, it's a lower pressure, higher volume pulse that allows you to effectively clean a longer bag length. So it allows you to go to the long bag design. The use of online cleaning, and online cleaning is important in a couple of areas. It tends to levelize the effect on the fan. You're not taking compartments out of service to clean. Typically a filter is always sold, a process filter is always sold with the provision that it can operate with at least one compartment out of service for maintenance. So if you have to clean offline and you've got to take a compartment out for cleaning and a compartment out for maintenance, it makes the overall filter size fairly large. If you can clean online, and this way you only have to take one compartment out for maintenance or allow for one compartment out for maintenance, again, it makes it a bit more cost effective. No bypass on startup. You guys have become completely unreasonable in that regard. It used to be easier to just say, hey, you know, bypass the filter until the process gas gets up to steady state conditions and then bring the filter online. That's not allowed much anymore. So you have to make provisions for startup procedures and the use of sacrificial compartments and I guess controlling at least or minimizing where the damage occurs comes into play. The use of the filter as a reactor, I mentioned previously, either primary or secondary. Primary in a couple of senses. I mean, you can actually buy bags that have catalysts or reactants impregnated in them, so reactions take place across the bags. Or what's very common now, obviously, is dry sorbent injection for knocking down acid gases, and you do get some in-flight capture depending on duct runs and residence times and chemistry. But with a fabric filter, you've got a lot of residence time where the material sits on the bags and the gas passes across the cake, and you get better reaction. Or secondary reactors, and there I'm sort of referring to what you see typically in a spray dryer baghouse situation. Most of the acid gas neutralization will occur in the spray dryer absorber itself, but you'll get a significant component across the fabric filter as well, maybe 15% of the overall gas removal. So they have that benefit. Again, we're seeing increasingly lower emission rates required for filter performance. And that has led to a more widespread use of PTFE membranes on top of the bag material itself to help ensure that the emissions are lower and lower. So pulse jet filters, typical device today, the tube sheets at the top, the bags are hung from the tube sheet. They're supported by internal cages because the gas is flowing outside in, so you don't want the bags to collapse, so you've got a bag with a cage inside of it. Most people, including ourselves, will use circular bags. There are other designs out there that other people use pocket bags, but most of the filters will use circular bags arranged in arrays. As I said, longer bag lengths becoming more common, 7 to 10 and even more meters in bag length. The bags now tend to be cleaned in those applications by a pulse of clean, dry air, drop down to 50 pounds or less with a higher volume per pulse. And you can do online cleaning, although with every filter, you can inevitably take a compartment offline and clean it down, and that's typically done, for instance, before you change bags. You'll take the compartment offline, knock off as much dust as you can to make the bag change easier to do. The bags are loaded from the top. You see here folks putting the bags in, so you take the bags and you put them in the tube sheet. There's usually some sort of snap band or other attachment mechanism. So the tube sheet supports the bag, and then you go ahead and drop the cage inside the bag, and with the longer bag lengths, multiple piece cages now have become more and more common. If you've got a 8-meter bag, you don't want to handle an 8-meter cage. The bag you can let unfold, but the cage has to be stood up, and plenums and roof enclosures have to be higher. So you tend to go with multiple piece cages that have some sort of connection mechanism. Cleaning systems, you've got a header with compressed air, which then, depending on the cleaning mechanism, releases the air into each row, and you can clean down each row. And with online cleaning, you're not just cleaning one compartment. You would typically, let's say if it's an 8-compartment bag house, you clean the first row in one compartment, then the first row in another compartment, so forth and so on until you went through all 8. Again, it tends to make the operation smoother, and in cases where you're relying on the filter for a reaction, that's important because you maintain the cake on the bags, and it helps smooth out the acid gas removal. Factors that affect the performance of a fabric filter, well, obviously the inlet gas conditions. The chemistry, the temperature, moisture content are important. The filtering velocity, or air to cloth ratio, which is basically the ratio of the volume of gas you want to clean to the square foot bag material that you have, or medium material that you have, is sort of the key design parameter for sizing fabric filters. The can velocity, how much of the gas is going to go upflow in the filter itself and re-entrain any material that could be cleaned off. Gas distribution within the filter itself, in terms of making sure you evenly distribute gas within the various compartments, and within each compartment adequately across all of the bags in the compartment itself, because you want to make use of all of the available surface area. So it typically involves a lot of modeling, almost always CFD modeling. Occasionally we still use physical models to do that. The nature of the incoming particulate, the amount, the size, the chemistry, in particular the chemistry, because it can affect what can happen in the bags. Whether you have material that is subject to spontaneous combustion in certain metals industries can be a factor. The distribution of the particulate, the particle size distribution in terms of rocks versus inhalable particulate. So you have to look at what bag material you choose and how you clean the filter down. And then typically that we'll go back into our caves and come back and say, all right, with all of that, we suggest or recommend that you use this filtering velocity and these numbers of modules or compartments, and here's the configuration. And typically it's either inline, or there's a header down the center that distributes it to 2 rows of compartments. Here's the bag configuration that we think you need, so many bags, this bag length. How we design the inlets, and I'll talk about that because it affects the performance of the filters. Whether you come in through the hopper and go up, or whether it's typical now with the long bag lengths, you come in from the side and use a distribution plate to distribute the gas and particulate, not all to the bottom, but across the bag surface itself. How you do the cleaning, what the tube sheet looks like. Bag material considerations. A lot of things affect, a lot of operating conditions affect what you can use for different types of materials: temperature, moisture, chemistry, abrasion resistance, the filtering mechanism itself. If you use a woven bag or a pure fabric, you tend to have depth filtration. So in essence, you're building up a cake, and a lot of the filtration occurs because of the cake that's built up on the bags. It's a little different than if you use a membrane. If you put a membrane layer on top, you have more of a surface filtration, less affected by the depth of the cake and that sort of thing. Common fabrics that are in use in different industries: polyester, acrylic, Nomex, PPS used to be Riton, now it's polyphenylene sulfide, something like that. Fiberglass, and PTFE. And the PTFE can be used either as a membrane on top of one of these other materials as a substrate, or in certain applications, certain cement kilns will use pure PTFE bags. It's PTFE on PTFE, so those are pricey bags. You want to make sure you treat them right, but they're very, very effective in what they can do. And there's a whole range of factors. I'm not going to go through everything here, but there's a whole range of factors you can go and look at, okay, depending on temperature and chemistry and moisture and whatnot, which materials make sense. But if you look at the column that says temperature ratings at the very end there, you'll see that for fabrics, the highest continuous temperature rating is about 500 degrees Fahrenheit, and that's fiberglass. So you're kind of limited there. If you've got a process that's got a higher temperature, you're going to have to control it before you go into a fabric filter or use a non-fabric medium. Designing filters for extremely low emissions, and this is becoming more and more common for us. We're seeing the emission limit requirements go way down. End up looking at the filtering velocity and maybe going with a lower filtering velocity than we would in other cases. That means a bigger filter. A lot of attention we pay to the gas distribution. Again, coming into the various compartments, within the compartments, we want to make sure that not only are we using all of the surface area, but we're not creating any problems. Typically with these long bag designs, you're hanging a bag maybe 10 meters off a support point. If you don't distribute the incoming gas and particulate correctly, if you bring it in, you can create a wind chime effect. The bags will swing. The bags swing, they rub together. They rub up against the internal stiffeners. They start to weaken at the tube sheet, and you get premature bag failure because of the abrasion that occurs, either at the top or where they're bumping up against other bags. Particulate distribution, minimizing any re-entrainment. Typical for very low emission rates now that we will go almost all the time to a PTFE membrane. And the bag cleaning mechanisms, again, very important. Got to have dry air, got to get the right pulse introduced, and you have to make sure that the pulse goes down the bag straight. You don't want the air jetting off to the side. You're going to not get an efficient cleaning mechanism. You're not going to go the full length of the bag. As I mentioned, there are some other more exotic devices that are out there from time to time, hybrid devices, and these are co-packs, essentially, a combination of an ESP and a fabric filter. We've done them, for instance, in cement kiln retrofits where somebody has had a 4-field ESP, very high dust loading coming in. They want to drop the emission rate. We keep the first couple of fields as functioning precipitator fields because you are knocking out a high percentage of the rocks that are coming in. The larger diameter particulate is coming down at a very high rate. So we reduce the loading on the last 2 fields, which we then convert to fabric filters and get the very low emission rate by using fabric filtration on the back end. If you were to stick with an ESP, you'd end up adding fields to get there. So this is another way to do that. Doesn't work in every application. There are certain applications where it works. Ceramic filters, again, specialized devices. They do allow for high temperature operation. You're using these ceramic candles. And the candles can be impregnated with catalyst. So you can turn them into not only particulate control devices, but reactors as well. And they're used to control NOx, dioxin, furan emissions, that sort of thing. One of the problems with ceramic candles is they're fairly heavy. So you end up limiting the length of the candle, which means you end up building out this way and you get a bigger device. But for certain applications, particularly metals applications where you're recovering a very valuable commodity, platinum dust, it's a good way to go. One of the other limits on ceramic filters is that moisture can damage the ceramic candles. So if you're looking at, for instance, at a boiler application, you want to make sure you don't have tube leaks. I'm not sure how exactly you do that exactly, but you have to worry about moisture getting over, whereas in furnace applications, glass furnaces, things like that, you don't really have moisture. so it's less of a concern. This is the hybrid precipitator fabric filter that I was talking about, one unit that we did. This was at a cement kiln. I just talked about that. The ceramic filters, you can go up to 500 degrees C. You get high temperature filtration. They are acid resistant, spark resistant, very high efficiency, get acid gas removal. So they definitely have some benefits in certain applications. As I said, there are some limits to them. They look a lot like pulse jet filters. You've got the elements hanging off the tube, but again, because these are ceramic elements, the tube sheet becomes not inconsequential, and typically you're limited to about a 3-meter bag or element length in this type of application. So it can make the filter a lot bigger. There's just a shot of this. This, I believe, was for a glass furnace application. In the agenda, there was one specific question about, or comment, I guess, about baghouse technology followed by wet ESPs for lead control. I have no experience with that specific configuration, so I don't know that I have anything meaningful to add there. I would be curious to know what application that was for. I don't know if the person that wrote the comment is in the room, but I'd be curious to know what that's for. My experience with lead is, as I said earlier, comes really from the incineration plants, where lead is regulated as a pollutant. Typically it's controlled in the fabric filter by the reduction of temperature. And it doesn't really condense, I guess. I'm not sure what the opposite of sublimation is, but it goes from vapor to solid, and it gets picked up on the bags there. So I'm sorry I can't provide a lot of a background on that specific issue. And that's it. Thank you for your time, and I'd be happy to answer any questions. I know we're running a little bit behind schedule, but yes, sir.
Mike, just a real quick question on a pulse jet.
Yeah.
Does the pulse of air go through the center of the bag and then force the dust on the outside off, or does it kind of go down the side and scrape it clean?
No, you want the pulse to go down the whole way and sort of create a pressure profile that will push the dust off the bags. Yeah, you do not want the pulse to be directed specifically at the bag. You want to make sure the pulse goes down straight, and certain designs will use venturis to introduce the pulse and help align it, because if the pulse hits the bags, you're going to get premature wear, and it won't ripple all the way down the full bag length, specifically with the long bags. Yes, sir?
Really, there's probably a lot of variability in the answer, but how often do you pulse down those tubes? I mean, like once an hour, once a day, once a week?
That depends on the process, and it depends on actually how you set the cleaning mechanism itself. In the old days, what you would do would be to set it on a pressure differential. So when the bag had been cleaned down, it might be, for instance, you might look at a pressure drop, say 6 inches across the tube sheet. And you would allow the cake to build up and the cleaning cycle to be initiated when it got to, say, 8 inches. You would clean it back down to 6. So you'd end up with this sawtooth pattern of pressure drop. You'd allow the cake to build up, you'd knock it down. You'd allow it to build up, you knock it down. That causes some disruptions sometimes with the operators, both in terms of it affects fan performance a little bit, and it, in cases where the filters are used as reactors, if you do it that way, what you're doing is taking all of the reagent off the bags. So people will try and levelize the cake thickness, and then you can do that either by cleaning these, as I was mentioning before. You clean this row in a compartment and clean that row in a compartment. Cleaning of fabric filters is always interesting with operators, because they tend to believe that why not just keep cleaning the darn thing. And some of them will go to constant clean. They will never shut it off. It actually damages the bags in the long run. So I think it's more common now. What we're seeing is people try to keep a constant pressure drop profile across the whole thing. So, but it does vary with process as to how frequently you clean it and how effective your process is working. You know, obviously, if you start building up material faster than you were supposed to, it may change process conditions. I think in this industry, one thing that's fairly common across technologies is that the operating conditions on any particular plant frequently don't resemble the design conditions. So you end up designing for one set of conditions and then find out that, oh hell, they're operating no way near that for a variety of reasons. Some of them are good reasons. I mean, you know, but yes, sir.
How long do you suggest to your clients to operate the bags before they evaluate their efficiency?
A typical guarantee on bag life these days ranges between 2 to 4 years. What we recommend to clients is that you almost immediately initiate a preventive maintenance program where you will periodically and regularly pull bags out of different compartments, different locations, and send them out for testing. You know, there's a variety of standard tests that the bag manufacturers will do regarding permeability and burst strength and whatnot, and compare them to what a new bag should look like. So you can sort of map how quickly the bags are degrading and whether or not that's a problem across your whole filter or whether it's localized. You've got certain compartments or rows within compartments that are seeing detrimental effects faster. So we like to recommend that you do that, you know, that the operator do that as a preventive maintenance program almost from the start. Typically, you have the new bags, and 6 months out, you should start the program.
And from the when they initially install a bag to when they do a performance test on that unit, would you suggest like 30 days, 15 days, 10 days?
We don't like to see that exceed 3 months. I mean, typically in our arrangements, we'll say, hey, you got to test within 3 months of installation. The shorter, the better.
A matter of days?
Well, I mean, if you install the bags correctly, I mean, they've got to be seasoned, and it depends on your process application. But I guess what I was getting at is you don't want to go into the field in a filter that you're building, install bags, and then allow a lot of work to go on around the filter itself. It should be sort of the last thing that you do, because you're going to end up with work gloves, welding rods, stray bolts, all that sort of stuff getting carried over, all of which are not normally good for bag material. So yeah.
I think just to expand on that, in the instance where you're waiting for a filter cake to build up to create the efficiency conditions you want, you would test after you achieve some sort of pressure drop across the device. Is that?
Yeah. You have to install the bags, and then you've got to condition the bag surface, and then you've got to get the unit up to steady state. There's probably different concerns and periods between if you're installing a whole new set of bags for first-time application, or if you're going in and you've got an 8-compartment filter. Depends on the operator. Some folks will go 4 years and change all 8 compartments. Others will say, no, we're going to change to a year and do it that way. So if you're only changing a compartment or something like that, it's probably a shorter time frame.
Touch on very briefly at the beginning, start on shutdown issues now. Are you seeing more interest? Do you have like a sacrificial bypass?
No, there's no bypass anymore. And those that have bypass ducts are pretty much welded shut. You have to direct, what is typical now is you direct the gas as the unit comes back online not through, again, let's take an 8-compartment filter. You don't put it through all 8 compartments. As you bring it online, you put it through 1, 2 compartments, but the sequence is the same. so that you know you're going to damage the bags prematurely, but rather than damage a compartment's worth of bags, you limit it or confine it. So, yes.
In the secondary aluminum industry, they use the line-coated fabric filters to control the acid gases, and they also use it to atmosphere. One of the facilities reported emitting ammonia. They actually injected ammonia into the system as well, in addition to their line-coated bag. Is that a common practice?
It's common if they're trying to do NOx removal. Why would they inject ammonia?
I don't know, this one
Yeah.
facility reported that on the information collection request we sent out. Figure out why they injected ammonia. In addition to what we already had.
I'm familiar with the use of lime injection in secondary aluminum. Ammonia would, if you're injecting, I don't know why you would inject ammonia unless you're trying to do some sort of NOx removal. You can inject ammonia as a reagent, but that's, if you're injecting lime, what's the point? And ammonia is going to go in as a gas, and it's not really going to get caught. The gaseous ammonia is not going to get caught in the filter, so it's either going to have to get reacted to some sort of ammonium salt, which it may not be. But
One facility reported that.
yeah, I don't have any insight there. Sir?
When you have a facility that wants to start doing DSI or activated carbon injection, how often do they run into air to cloth ratio issues or needing to resize bag gas?
The question is, if somebody has a fabric filter and they want to use DSI or activated carbon, what impact does it have on baghouse sizing? Is that what you? Let me break that into two categories. For dry sorbent injection, typically all you're doing is increasing the grain loading. And in most cases, you shouldn't need to increase the overall filter size. If you're looking at carbon injection, you have to take care as to whether you are collecting the carbon in conjunction with fly ash or other material, or you're removing the fly ash and just collecting the carbon. Just collecting the carbon is a more specialized application, and you do have to worry about hopper fires. But if you look at, for instance, a boiler, the amount of, in most cases, the amount of fly ash relative to certainly carbon, which is a pretty low rate, you don't see it. For sorbent injection, if you're injecting to knock down SO3, again, it's a fairly low rate. If you're injecting to do some sort of desulfurization, it depends on how much desulfurization you're doing, what sorbent you're using, and how much, essentially the stoichiometry, the amount of alkali that they're putting in. I guess in extreme cases, that could have impact baghouse sizing. I might be more worried about the ash handling system and overloading that, first off. Yeah, I guess those situations are out there. I mean, typically, at some point you say, if you're going to put that much dry sorbent in, why don't you just go to a scrubber? You'd be better off because, just the whole operating capital cost trade-off. But certainly it depends on the amount you're putting in. In most cases, it's not that high. It's more trim desulfurization, if I put it that way, or acid gas removal. Or at least that's what we've seen. Thank you.